You're inching these weights closer and closer to something in a bin. But it means that these guys are all like then related, like they're in for the long haul together, unless they jump bins, which is of course possible as well. Yeah.
I think maybe an argument for this is that you cannot assume that the centroid is the mean of the points which are associated with it.
Yeah.
And then when you compute the gradient, it makes sense that it should be the mean of the gradient as well.
Of course, I mean average pooling kind of works the same.
That would be the idea.
Yeah. I think that's a.
I would put a different perspective on it. Basically, this is very similar to compressing, to using, for example, how you convert the emission to fixed scalar or fixed palette, basically. They also use K-means clustering to basically do that. So this is basically just the idea of treating these weights as an image. And like applying gift compression on it.
Absolutely. It's a similar type of idea. I don't know that much about that form of compression, but the interesting thing to me is that at least in an image you have like, I need to learn more about that compression to really respond, but the image of course has local similarity between pixels. Like the pixels are distributed in a way, like if you have pink here, there's a high probability that like the next door neighbor will be kind of close to that. Whereas weights are distributed in a pretty, or at least there's no underlying function that can easily explain that.
So you did do that without the compression. These blue ones will stay close to each other. Will stay close to each other after training?
It's a really good question.
Because I was thinking like you're sort of, just because they're close together right now doesn't mean that with continuous training they will stay close.
Absolutely.
So
I mean,
now you're forcing them to stay.
I think the intuition of that is because you've already baked this in the oven for 7 days. The fact that they're close.
So this is completely after training. So it's not each.
Exactly.
It's not
No. It's after training, then you start doing this.
This is a local minimum that you pick.
The central.
You maybe jump into another local minimum and you continue with
But it only works after fully training it. I know of no libraries that out of the box do this. How many of you guys, just show of hands, how many of you guys, irrespective of your job setting, would rather be using PyTorch than TensorFlow on any given day?
Yay.
Great. Okay, me too. How many of you guys are the opposite?
thrown out.
How many of you guys are the opposite? It's okay. You can. Now nobody wants to raise their hands. Thanks a lot. No, I'm totally that way too. Oh, bravo. Okay. I guess you use assembly and you use C, right? So congratulations. I mean, my company Meeshkan is a PyTorch house, but that's because there's 4 of us, and like we can do whatever we want. But and by the way, did you guys see that 1.0 is now like officially?
Yeah, 2 days ago.
Woo! Yeah, exactly. So use it if you haven't used it yet. PyTorch. The really nice thing about it, or bad if you're like me, is that you can mess with the gradients because it has this autograd thing. So you could literally ingradient descent just and do whatever you want. In TensorFlow, I guess you could do that. Somebody told me you could recently. I just haven't figured out how. But in PyTorch, it's super easy. So anytime that you want to be messing around with the gradients and what the weights are doing, do it in PyTorch. Of course, the negative thing is that you might need to take them off of the GPU, right, to do the manipulation on the CPU and then throw them back on the GPU, and that takes time. But if you have time, then that's a valuable thing to do. And of course, if you can do all this on the GPU, then it's even faster. So,
a short addition, isn't this supported out of the box in TensorFlow? I'm all for PyTorch, but I mean, in TensorFlow you can train your graph and then afterwards do like TF quantize tool and just...
But does TF quantize do this? So
doesn't it do
clustering?
That's perhaps my question.
I don't know.
Well,
maybe somebody could look up TF quantize right now. Yeah, it's worth looking up. I mean, maybe it does actually. Yeah.
Probably it doesn't because we lost a huge deal of accuracy on it.
Although, I mean, to be fair, once you start doing this, your model like gets worse before it gets better, which you could probably imagine. It takes a large leap of faith to start doing it, but yeah.
As with the epsilons, wouldn't this be a sign actually that you have a lot of redundancy in the network?
I don't know, because
it's a general statement with any kind of network.
I mean, all machine learning, of course. I mean, you guys, like, it's kind of trivial to say this, but it's just a giant pile of linear algebra that you start until it resembles a function. So it like there's going to be redundancy just because it's a giant pile of linear algebra. I mean, I think that all machine learning networks need to be necessarily kind of redundant, just because the function that they're approximating, in theory, well, always needs to be smaller than them. Otherwise, you can encapsulate it. So it's like a philosophical question, I guess, more than anything else. But
Yeah, but wouldn't you be able to choose a network that would...
that would encapsulate better. Yeah, sure. I mean,
those are much harder to train. I mean, the variance in training tends to go down with the model size. I suppose that's why we have so over-parameterized networks as it is. I mean,
yeah.
ever since AlexNet, we've already worked with 100 times more parameters than we've ever needed.
Yeah.
And now we're up in millions.
Yeah, absolutely. And it doesn't show any signs of stopping. Because otherwise, how else would Google sell their TPUs? I mean, they have. Did I say that?
Yeah.
So,
Okay, so this would actually be the easy way out. I put more parameters than I need, and then I just let it train away, and then I quantize it afterwards, and I don't have to
Isn't that
think about
what we did
how to
last
widen it.
4
I mean,
years?
people do that with their health too. They like go on binges and they go like a 2-week thing where they lose it all, and it's like it works. But people have meat. But yeah, that's totally I mean, yeah, absolutely, that's a way to do it. And it just depends how much hardware you can throw at something at the end of the day.
I
But
suppose that's why distillation also works. Like you train a big network and then use that big network to train a small network, and
Yeah.
that small network is better
Yeah.
than if you train it from scratch.
yeah, I mean that's the classic thing. Like it takes what is it? Less time to build a 4-inch and then a 6-inch mirror than a 6-inch mirror. So I mean, it totally, yeah. It's I mean it depends. It's a philosophical thing, right? It's a business argument too of like how much GPU and CPU you have. Of course, if you want to follow this training, like one great way to do it is on the Meeshkan tool. If you guys want to sign up for that, Meeshkan.com. I digress. But the most important thing is just to know that this works. And like I don't know of a single thing that implements it out of the box, but convince yourselves that this is not hard to do, right? I mean, doing k-means clustering requires downloading scikit-learn. We all agree? And then like, after that, it's just a subtraction. So it's really like, it's just underutilized in the deep learning community. I say community, like, let me back up. I'm like the most antisocial nerd in the world, so I don't have like a broad sense of what people are actually doing, but at least in the projects that I've worked in, nobody's ever used this. I've used it successfully once to reduce neural network size, and really has worked. So that's the weight sharing algorithm, and now let me get a little bit the way that it's done, and then I'll get to initialization. Why does it not? Okay, actually talk about this here. So first do k-means clustering on the weights in order to break them into n bins. That's like pretty trivial. But of course, what are those bins, right? So you need to initialize the first centroid. So that's really, because after that, then you're just multiplying by the gradient and by the learning rate, and then it converges towards something. But you still need to choose the right initialization. So all of you guys know that weight initialization, like, if you don't do it right, it just screws everything up. It's like the easiest way to tank your neural network, along with like a really terrible learning rate. And same with this. Like, if you don't initialize the centroids right, you'll totally screw it up. I know this from experience. So they suggest a couple things. One, what I would have initially thought, but it actually just winds up being totally wrong, so I'll explain why I thought it and then why I was wrong, is to, it seemed kind of obvious to me in the beginning, take all the weights, right, find out what the actual centroids are of like for example, if you have a histogram of the weights, and you have like a cluster of them around 0 and a cluster of them around 0.2, it would make sense to have maybe like 2 bins with 2 centroids that are there. Meaning look at the weights as they've already been trained, and then pick the centroids based on the distribution of the weights. Does that sound like reasonable to most people here? Yeah,
Like
it's totally wrong. But that's,
manually looking.
yeah,
Manually
or I mean just doing some type of analysis on the weights to see like where the mean is of, or like what kind of local means are, and then going from there. So that's like, or using unsupervised learning to look at some type of clustering of the weights. That actually turns out to be a terrible idea, and I was like shocked by why, but then I realized like it totally makes sense. So in a neural network, most weights will be pretty close to 0. So if you're looking at the random histogram, or the histogram that describes the weights, the centroids, if you use the method I just described, will be close to
0.
And the problem is that if you want to actually capture weights that matter, you want weights that are not close to.
Wow.
Thank you. You're really good at that. So the problem is that if you just zoom in on where the weights actually are, then you're not capturing the outliers with your centroids, which is what you actually care about if you're spending the time to do this to begin with, right? Seems kind of obvious, except like I didn't think about it, but like that's why I'm not a researcher, right? Because these people did. So the way that they do the initialization of the centroids is linear initialization across the weight space, which of course is probably going to be between 0 and 1. I mean, assuming that you're using some type of like gradient clipping for stuff that goes out of control or like whatever, it's still going to be like in that bound, right? So what they do is they distribute the centroids. Assume that you have n bins, like n is 3, then it's 0, 0.3, 0.6, like whatever. Or no, I mean just shift that by 1/6, but you guys get the idea. It's like distributed over the space. That's way better because you'll have a centroid that is closer out to the weights that actually matter. So linear initialization across the entire range of possible weights, which is interesting because of course when you're doing actual, like the real weight initialization is random initialization, right? You would never do linear initialization of weights. It doesn't work. So this was a surprising outcome, but I think it's a really important one to know when you're doing this sort of thing. So moving on, the last thing that they do is Huffman coding. How many of you guys know the Huffman coding algorithms? Yeah, I mean, they're like pretty standard and boring, right? Like they're in the JPEG, or like most zip backends use Huffman. There's like if you go to Rosetta code, there's like 20 lines of code you could do Huffman coding. I don't really know the most efficient way to do it, and I'm not claiming that this project is, but it exists on PyP. Use it. So the genius of using Huffman coding, because at first I was like, this is like super old and like why? If you're quantizing to different centroids, right, then these centroids just become letters in your vocabulary, right? Because your weights can only be one of n things. And then Huffman coding totally makes sense because Huffman coding finds repeated occurrences of a thing and assigns them an index in some type of hash function. So if you're, let me go back to Huffman coding for a second. Assume that you didn't do some type of weight quantization based on centroids. Assume instead your quantization was the naive aliasing one. The weights would be all over the place within the space that you're aliasing to. And as a result, Huffman coding wouldn't really work, meaning you'd have to have you would have to have a code for every single possible weight. Like if you had 5 bits, it would be 2 to the 5, and then at that point, why even do Huffman coding? Because you're doing a code for the entire space, which is as big as the space. Here, because your weights can only be a certain number of things, then it makes sense to use the Huffman coding and just count how many times they show up. So basically, the weight sharing algorithm is the thing that makes Huffman coding possible here, which then gets the network even smaller. So it's like this really cool 1-2 punch. Yeah.
Would you use other compressions like LZW?
No comments, just because I'm not an expert on compression.
And that was like behind GIF, and GIF's like regular structures, so maybe that might
I
work.
think without context, Hoffman is optimal.
What was the question?
LZW?
It's also
Because it's mathematically optimal. So Hoffman is basically if you have a set of symbols, you assign a shorter bit representation of that symbol based on the frequency of the symbol, right? So, and you're doing it in a mathematically optimal way. So, if you have 50% of all the words or all the symbols are A, that will get a really, really short representation by probably just a 0 or something. And then the rest will get,
I see what you mean.
yeah, the rest of the symbols will get started with a 1. So you know that this is not an A symbol, and then you have to start like, so that's supposed to be optimal. Like information theory wise, if it's the correct distribution of, let's see, the letters, the symbols that you're encoding with, then it's optimal. So. But you can do better if you have context and you have repetitions and kind of weird stuff. But it's, like, but without context, it's optimal. So.
Exactly, and I think we can all agree that this doesn't. I mean, there's no context for these weight. Interesting, of course. They're just kind of gobbledygook. And the other thing is they have these letters, which are the centroids, which is what you're leaning towards. So it's kind of like when I read that, I said, that makes sense, and you get more bang for your buck because the weight quantization method allows Huffman coding to then be applied afterwards, which is just like a really cool find. So they do this. Then pure awesomeness number one, accuracy and size. So this is just me, like, you know, my little, I copied and pasted from the paper, but it's just worth seeing. So this is how much they squeeze down the stuff, which is pretty rad by applying all of these things. I mean, that's like really small, right? I mean, VGG 16 is like, that's crazy. So we're talking about massive compression factor. Like, this goes from like Apple banning you from iTunes to like 1 million downloads, right? I mean, it's a huge thing. So that's where the power of all this stuff really comes in. And then, of course, the error. This I think is a little bit cheating in that I don't know why they. Like, basically they only put things that work better than before. That's kind of like, I don't know, I'm sure they like cherry picked the best results.
Have you tried it?
Yeah, it never works better than before. But like, whatever. It's still, I mean, it depends what the business case
But
is.
in the cases you tried it, how much, I mean, was the accuracy affected a lot?
I mean, like, within a couple percent points, you'll totally get there. I mean, the thing that sucks is that I haven't figured out yet, but this is like my shortcoming as an engineer, is how to keep it all in the GPU, because to do all of these things, I have PyTorch writing back to the CPU, doing, like, for example, the centroid and clustering on the CPU and then back, so it just takes a lot longer than if you have a full network running on the GPU, unfortunately. But that's my shortcoming, not the algorithm's shortcoming. So, but yeah, it totally works, and I used it. If you guys don't know, I took it off of Google Play, but do you guys know what Arctic 15 is? It's a conference kind of like Slush. Do you guys know what Slush is? Slush is like a thing in Finland where I come from. And so Arctic, or I don't come from there, but I wound up there because I took the wrong plane. But Arctic 15 is a conference that's also in Finland. We made, as a joke, an investor detector for Arctic 15 where you could hold up a phone and detect if the person was an investor or not with like image recognition. It got a lot of traction actually. But yeah, that's where I've used this in production. And it totally worked. So yeah, I mean, it was what allowed us to essentially but that was, I mean, in May, and I've heard that TensorFlow Lite has gotten a lot better since then. I don't know if you guys have used it recently.
And you got the same compression factors, so range-ish.
No, but it was like, I mean, maybe an order of like 10.
Oh, but still.
Yeah, awesome. It's just, these are close to like 20 to 100 even. But still, yeah, absolutely. But like I said, it just took a long time to train. But that's actually when I got into this. I found this paper precisely because we had the problem that we had a way too large network because I didn't have time to train a small one. Yeah.
So if you don't have the model in memory on your phone, for example, and you decompress the model, is that like something you do during inference? Like,
It's a
and does that take time?
really good question. The way that we did, the way that we did it actually was working with, so it depended on kind of what stage of the process was, but keeping it in compressed form for the sparse matrices. So we didn't decompress and deflate it, and that's a big thing that the authors don't talk about, but that's like the $1 million question, right? Because if even if it's compressed, if you have to scale it up again to be able to run the inference algorithm, then like it may as well not be compressed. So we kept it in a sparse form, but it actually didn't slow down inference that much for what we needed. It's like that still has to be figured out by the community.
But is it is it decompressed to a sparse form where there are actually floating points again, or is it decompressed into a sparse form which has this which centroid index?
No, it's decompressed into a sparse form where it fills in the centroid, but still it's pretty sparse at the end of the day, because most of the things are 0, right? But it essentially desparsifies it a little bit by physically filling in the centroid, instead of having a hash function that points to the centroid. To be honest, I didn't even try that because like I had like days to put this together. I mean, it was like for a gag, right? But but that could work. I mean, it's entirely possible that you can literally keep it that compressed and then just call the index function.
But use TF lights, or was it on own inference on you?
It was it was using partially using TensorFlow Lite, but back in May at least,
Yeah.
It was like pretty hopelessly broken, at least for what I wanted to do with it. But I don't know if you guys have used it with success since then.
I've heard lots of people using it without success.
Yeah, that was me. Yeah, which is why I did this whole thing.
So, I'm sorry, can you tell me if this question is really off the point? But so, in the beginning you said it's forbidden to make this word compression because you get all sorts of really weird effects. And I don't really get it now, because if we use this centroids, it sort of sounds really a lot like word compression to me. But
yeah, I mean, let's go back for a second to the difference. So the difference with them, there's a couple things, but one is that the word compression fixes, let me go back, that if you use word compression, there's a notion of kind of random rounding up or down. Like let's say that you didn't have the back propagation, right?
Okay.
So you didn't do any of this. Then you're not multiplying anything by a learning rate, and you're just kind of essentially gets rid of this, and then you're just rounding these up and down to the closest thing.
Yeah.
Whereas this is an iterative process, like that essentially replicates training, right? So maybe that's the extra thing that adds in. That's one, and two is that word compression. Even if you cut this out, the nice thing about the centroids is that it allows you to. Well, I mean, this is a technical implementation thing, but usually when you do word size stuff, you're compressing it to things that the compiler knows about, so like unsigned integers or like signed integers or stuff like that. And here, at least in the implementation they use, of course, this knows nothing about any type of representation of numbers. So it's just you spread as many bins as you want, and then you create your own numeric representation of what those words are. But that's kind of the trivial answer. The real answer is because it has the same gradient descent process as the actual training system.
How many centroids would you use in like some typical scenario?
For
example, in your case?
Half, but here they use, they actually give an equation for how to figure that out, but in the paper they talk about going down from, so when I say half, I mean I went from 32 to 16, but they went from 32 to 5 bits, so 5, which is pretty bold, yeah.
So do they have a discussion about the size of the data set they train on? Because I think this is conditioned on having a big data set.
I think they talk about CFAR 10, if I'm not mistaken. I have to go exactly to the paper. And
Because I think this is conditioned on having a flat solution space, right? Where you can move in arbitrary directions around the minima, you will change the solution like that. If you have a small data set or in a spiky solution space,
yeah, my gut kind of says that too. I mean, but that's more from experience that like, if you have a really biased data set, like if you're doing something like detection of a anomaly, then stuff like this might not work as well. Yeah.
5-minute leg structure.
Yes, absolutely. Sorry.
This is super interesting.
Yeah. Let's stretch our legs.
Go to the toilet.
And then like because we're not. Yeah, leg, beer, and chat, and yeah. Then we'll come back into this. Thank you.